Professor Abdul Rahman, are you ready? Professor, do you hear me?
Yeah.
Are you ready?
Yes, I'm ready.
Okay, I am starting your presentation.
Okay. Thank you. Okay, good afternoon. So today I will present my research on the study of the effect of radiation on the flow and heat transfer characteristic of hybrid nanofluid. My name is Mohd Rosdzimin Abdul Rahman. I'm from the Universiti Pertahanan Nasional Malaysia, from Malaysia. Okay, first I would like to present the introduction of the project overview. So we know that the heat exchanger is required special coolant to enhance the thermal performance, and this exchanger is required for the space application, environmental engineering, electronics, industry, manufacturing, and industry heating and air conditioning device. to This coolant also need to stimulate the convection transfer, where we need the special fluid that can enhance the performance of the heat transfer. So this study required to study the effect of the different number, nanoparticle volume percentage on the presence of the radiation. Okay, the problem statement. Uh, Currently, with the advancement of the electronic devices, with the increase in power capacity, thus this electronic will produce the excessive heat. So it is an issue to maintain the working temperature, especially in the tropical country, where we have uh, the temperate and dry condition, and sometimes the temperature is going high. So we need to maintain the working temperature of the device, because if the device working for a long period in extreme condition and the temperature reach the exceed the maximum working temperature, then the device will shut down. So that's why we require a special fluid that we can uh, use to enhance the performance of the heat exchanger to cool to reduce the temperature of the electronic devices. Okay, the objective of this study is to investigate the flow characteristic and to investigate the heat transfer performance. The scope, so we are using the circular tube by focusing on the laminar flow and at various nanoparticle volume concentration. And also we introduce the radiation effect, and this tube is uniformly heated. The particle that we use in this study is the uh, cuprum and copper and aluminum oxide. These two nanoparticle will mix to make a hybrid nanoparticle. So the volume percentage that we're going to study is from the 0.04, 0.06, 0.08, 0.1, 0.4, 0.6, 0.8, 1, 2, and 4. The inlet temperature is maintained at 27 degrees C, and the uniform heat flux is make it constant with a value of 9,549.29. This is the geometry and boundary condition of the numerical domain. We're using the two-dimensional symmetry aluminum tube. The length of the tube is 1000 mm and the diameter is 10 mm. So we have the axis symmetry when because we need to reduce the computation time in order to get the better result. Okay, this is the water and nanoparticle thermal properties. Okay, for water, we are using 997.1 kilogram per meter cube density. CP is 4179 and thermal conductivity is 0.613 with the viscosity of 0.00855 and Prandtl number is 5.85. For the alumina, the density is 3,970 and CP is 765 with the thermal conductivity of 35 and the particle diameter is 47 nanometer. And also for the copper, the density is 8,933 with a CP of 385, thermal conductivity 401, and the nanoparticle diameter is 15 nanometer. So this property, we refer to the Shikoleslami et al. 2013. Okay, to calculate the density of the hybrid nanofluid, we are using two models. The first model is the Hamilton-Crosser model. This is the equation that we are using to calculate the density of the hybrid nanofluid and also the CP. Okay, the Hamilton-Crosser model are using the shape factor. Okay, so the M value in this equation for the thermal conductivity is the shape factor. In this study, we consider the shape factor is sphere. Only one type of shape factor that we are using is sphere. Okay, the second model that we are using is Kuh and Klesterer model, because we want to see the effect of the Brownian. In the previous model, HC model, the Brownian effect is not considered. And in the Kuh and Klesterer model or KKM model, the Brownian effect is considered to study the effect of thermal conductivity. Okay, this is the equation that we're using to calculate the thermal conductivity of the hybrid nanofluid. This is the viscosity, where the KKM model is taking the effect of the Brownian. And the radiation model that we use in this analysis is the Rosland model. This is the well-known model to study the effect of radiation in this simulation. Firstly, we are conducting the mesh independent study. We change the various size of the mesh because we want to find the lowest mesh that the result is not changing to use for the all simulation. In the study, we're using the 1000 times 10 size of the mesh, because as we can see from this figure, this is the velocity magnitude at the outlet, whereby the profile of the velocity is not changed significantly, even though we increase the number of mesh. So to reduce the computation time, we're using 1000 times 10 mesh. Okay, so now I will go to the result and the discussion. Firstly, we validate this numerical. This present work with the experimental result by Suarez et al. 2012. So our uh, model is agreed with the experimental result of the Suarez. For this case, for the validation, we are using water. Later, then we validate these two model, KKL and HC model, with also the experimental by Suarez et al. For the nanofluid alumina with water. So here we can see that the KKL model and HC model using the sphere type is not significantly different, but some deviation from the experimental result at the Reynolds number of 1005 and above. But in this case, we consider it still agree with the experimental result. So, and also for the friction factor, the profile of the friction factor is follow the profile of the experimental result. Now is the result of the hybrid nanofluid from our model, and we compare with the experimental result by Suarez et al. So for the model KKL and HC, they have a huge deviation between these two models. For the KKL model, the line of the numerical is higher than the experimental, and for the HC sphere is lower than the experimental result. But the deviation from the experimental result is less for the KKL compared to HC. Therefore, we are using the KKL model throughout the simulation to study the effect of the radiation and also the effect of nanoparticle concentration. Okay, then we include the effect of the radiation. We can see for both models, we're using KKL and with and without the radiation. You can see when we add the radiation, the result is higher compared to the model without the radiation. So the radiation is significantly affect the result of the Nusselt number at various number for the hybrid nanofluid. And for the friction factor, there's no difference between the hybrid nanofluid with radiation and without the radiation. As we know that the radiation will affect the heat transfer, but not the flow characteristic. That's why the friction factor shows this is no significant difference. There's no difference between the model with radiation and without the radiation. Okay, now we study the effect of concentration and radiation. Firstly, the effect of the nanoparticle at the concentration very constant with the number without the radiation. Okay, we change the concentration 0.04, 0.06, 0.08, 0.0, 0.1, 0.4, 0.6, 0.8, 1, 2, and 4 concentration. So at lower concentration of the hybrid nanofluid 0.04 to 0.08, we can see the difference is very small, even though there is the increase in the Nusselt number when you increase the concentration of the hybrid nanofluid. Later, when we increase the volume concentration 0.1 to 0.8, also we can see the effect of the concentration on the Nusselt number. And also the deviation, the range of the changes from 0.4 to 0.6 is larger than 0.04 to 0.06. So this you can expect since the order of the concentration is increased 10%. And for the volume concentration 1%, 2%, and 4%, we can see the deviation is large. Again, we increase the volume, the order of the volume concentration, and the variation is very large. So the effect is clearly seen here when we change the order of the concentration and the various concentration that we use for the hybrid nanofluid. This is without the radiation. And it also shows the similar trend for the friction factor. So at higher volume concentration, the friction factor is high. So this is because the number of increase in the density and viscosity of the hybrid nanofluid will increase the friction factor, and that's why then we need the more pumping power to make the system works. So even though we can increase the Nusselt number at higher volume concentration, but the drawback effect on the friction factor we need to consider. And this is the result for the radiation, hybrid nanofluid with radiation. We can see when we increase the volume concentration, the Nusselt number also increase, and the order of the volume concentration also affect the result of the Nusselt number. And the result of the hybrid nanofluid with and without the radiation show a significant difference. We can see here the here the Nusselt number, the highest Nusselt number for the hybrid nanofluid variation is more than 100, but for the previous, we can see the higher Nusselt number for the hybrid nanofluid with the duration is only 70, and with the duration is more than 100. So the effect of duration is significantly seen in this result. And we can see also at the the order of 0.01, the variation in the volume concentration is low compared to the 0.1 order volume concentration. Also, this is 1 order of volume concentration. So, and this is the result of the friction factor. Also, the similar trend we can see when we increase the volume concentration, the friction factor also increase. And this is all the result. And now this is the conclusion for the study. So we can see here that the KKL and HC model are agree with this result. But compare both model with this result, they show that the KKL model shows small deviation from the experimental result compared to HC model. Then throughout the simulation, we are using the KKL model. So for our objective, we have two objectives. The first objective to investigate the flow characteristic. So the outcome, we can conclude that the friction factor decrease as increase in the Reynolds number for various hybrid nanofluid, and also increase in hybrid nanoparticle or increase the friction factor. And inclusion of the radiation is, this is we know that the radiation will affect the Nusselt number, not the friction factor. And for the objective number 2, to investigate heat transfer performance, the outcome that we found that the Nusselt number increased as the hybrid nanoparticle volume concentration increased. And the Nusselt number increased with the inclusion of the radiation. So for overall, we can conclude that radiation, radiation show the significant effect on the thermal performance in the hybrid nanofluid. Okay, thank you. So that's the end of my presentation.
Thank you, Professor Abdul Rahman, for the study on hybrid nanofluid exposed to radiation and heat generation presentation. It was very nice and very interesting, I think. Just now, I want to ask to all of our participants, do you have any question? If you do you have any question, you can write your questions to chat part, or if you want to ask your questions by yourself to Professor Abdul Rahman, please write here, write the chat part about you have a question, and after that we can open the open your system voice and you can ask your questions by yourself. Professor, we can wait a few minutes for questions.
Okay, sure.
I think there is no question for now. Sorry. Fine. Professor, there's a question for you. I think Professor Samasora want to ask your question by yourself. Professor, we are listening to you.
Okay. Temperature variation. Actually, for the inlet, we just set at the 27 degree C, and we set the uniform at the outer wall. So to get the range of the variation, maybe I can, because I don't have the data with me now, so maybe I can reply to you, maybe through email, maybe I can share the result of the temperature range.
Okay, thank you. And I have another question. On your simulation, the conductivity, did you put a constant value of conductivity?
For the thermal conductivity?
Yes.
Yes. The thermal conductivity is not the temperature dependence.
Okay. Okay, thank you.
Yeah. Thank you for the question.
If anyone have any question, we can take another question just now. Yes, I think for now there is no another question. Thank you, Professor, again for your presentation.
Okay, thank you for the organizer.
You're welcome. And also, if any participant want to ask another question about this presentation, you can send an email to Professor Abdul Rahman. Thank you. And now we are going to watch another presentation from NFM conference. One of the invited speaker, Professor Aldona Balcinaite, as a pre-recording from the Center for Physical Sciences and Technology from Latvia. The title is going to be Synthesis and Characterization of Different Catalyzers for Alkaline Fuel Cells. But we have time. We should go according to our time schedule. 5 minutes for coffee break. After that, we are going to start Professor Aldano's presentation, and it's going to be our last section.